Welcome to This Explainer. Today, we're diving into a really wild machine learning paradox. It's this fascinating concept that explains why throwing more and more data at a problem can actually, completely destroy your results. It goes against almost everything we're taught to believe about information. But by the end of our time today, you'll understand exactly why this happens and, more importantly, how to fix it.
So, we're human, right? And humans naturally assume that more information is always better. Like, if you're trying to predict the weather, you'd want every possible measurement: temperature, humidity, wind speed, the migration patterns of local pigeons, what the meteorologist had for breakfast, the whole shebang. But we're going to flip that intuition completely on its head today. In the world of machine learning, piling on more features or more variables doesn't automatically guarantee a better model. Actually, scratch that. It can literally derail the entire thing.
We call this paradox the curse of dimensionality. Think of it kind of like a monster that just feeds on your computer's memory and spits out pure noise. As you add more dimensions, meaning more variables or features to your dataset, the overall space your data lives in grows exponentially. Suddenly, all your data points are incredibly spread out, and the underlying structure of your information just starts to collapse. To really wrap our heads around this curse and pace ourselves, we're going to group the symptoms into three logical buckets: the learning problem, the hardware problem, and the human problem.
All right, let's jump straight into symptom number one, the learning problem.
Here's the deal. When you have too many variables, they actively prevent your machine learning models from finding meaningful patterns. In low dimensions, when you just have a few key variables, your data sits in this nice, dense, structured space. Patterns are super easy for a computer to spot. But as those dimensions grow into the hundreds or thousands, the data points become incredibly far apart. We call this data sparsity. You're basically turning a bustling, structured city into an isolated, sparse wasteland, where data points are so distant from one another that the patterns just vanish. And because of that sparsity, we run smack into a massive issue: overfitting. You see, when there are way too many variables and the pressure of small sample sizes, meaning you just don't have enough rows of data to fill up that massive new space, the model panics. It resorts to overfitting. It merely memorizes useless noise and weak features instead of actually learning reliable, generalizable patterns. It's exactly like a student who memorizes the answers to a practice test but completely bombs the actual exam because they never learned the underlying subject. Okay, so that's the learning side. Let's look at symptom number two, the hardware problem. This curse isn't just theoretical math. Every single dimension you add carries a very real, heavy physical cost. The computational burden just compounds. More dimensions mean vastly more calculations. Your system needs significantly greater memory just for basic storage. Then you need even higher memory for data preprocessing. And finally, drastically increased demands during the actual model training and prediction phases. The model just has way too many inputs to juggle at every single step. So the crucial point here is that this complexity creates immense real-world friction. When your system is bogged down by thousands of variables, you're looking at longer training times, way slower experimentation, and sky-high hardware demands. If you're working with large data sets or systems with limited resources, this leads directly to a much less efficient deployment. It literally slows down your entire cycle of innovation. And finally, we face symptom number three, the human and analysis problem. This is where the mathematical foundation of our models, and really our own ability to understand them, begins to completely break down. You know that lots of machine learning methods rely heavily on distance metrics to group things together, right? Well, in high-dimensional spaces, those distances between points become way less meaningful. Because the space is so vast and sparse, every single data point starts to seem equally distant from all the others. And if everything is far away, the whole concept of closeness or similarity completely loses its value. And look, if the machine cannot effectively measure distance, humans certainly cannot visualize these patterns. We live in a three-dimensional world. Trying to mentally picture or plot a data set with 5,000 dimensions? No way. It's physically impossible and will just give you a massive headache. The curse of dimensionality strips away our ability to plot the data, which directly robs us of our ability to interpret it, communicate it, or understand what's actually going on. All right, now that we definitely feel the pain of this curse, let's shift gears from chaos to clarity and introduce the cure. Dimensionality reduction is this really elegant solution. It's all about extracting the pure signal from the noise. It literally means reducing the number of variables in a dataset, but And this is absolutely crucial, doing it while keeping the most useful, relevant information intact. It's what makes learning practical, efficient, and ultimately way more effective. Think about it practically. Would you rather have 50 strong, highly predictive features or 5,000 weak, noisy ones? A model built on those 50 highly relevant features is just vastly superior. It's going to train faster, use less memory, and find much more reliable patterns than a model that's just drowning in a sea of 5,000 weak variables. Now, a quick caveat. You have to remember, this isn't about blindly throwing away data just to make your file size smaller. That is a huge trap. If we remove too much, or if we just delete variables randomly, the model simply becomes less accurate because we've thrown out the signal right along with the noise. The true goal is to preserve the useful patterns, the underlying relationships, and those critical predictive signals. So, how do we actually do that? It boils down to a straightforward, actionable process. By removing weak or redundant features, creatively combining related information, and strictly keeping the most relevant attributes, we hit a perfect balance. We're balancing two massive ideas here, effectively reducing that crushing mathematical complexity while strictly preserving the essential underlying structure of the data. And when you do that, dimensionality reduction directly neutralizes every single challenge we talked about today. Where we once had overfitting, we now have simpler, more generalizable models. Where sparsity hit our patterns, reduction makes the space dense and manageable again. Those high hardware costs, slashed, improving efficiency. And those weak, meaningless distances are replaced with clear, interpretable analysis. It solves the curse across the board. I want to leave you with a real-world scenario to think about. Imagine you're working with a medical data set. You've got thousands of patient variables, blood pressure, genetic markers, heart rates, but only a very limited number of actual patient records. We know now that feeding all of that directly into a model is a guaranteed recipe for overfitting and total failure. So, armed with what we've covered today, how would you personally extract the signal from the noise when patient lives are actually on the line? Think about how you would apply dimensionality reduction to find the truth hidden inside that data. Thanks so much for joining me for this explainer, and keep exploring.